You know, it's fascinating. Every child who has ever blown a soap bubble has witnessed one of the most profound demonstrations of quantum mechanics, molecular forces, and mathematical optimization, and they had absolutely no idea. They just saw something beautiful and round floating in the air. But here's what will collapse your logic. That bubble knows more physics than most physics students. It's solving differential equations in real time. It's minimizing energy functions. It's balancing forces at the molecular level. And it's doing all of this without thinking, without calculating, without even trying. I'm going to tell you something that sounds impossible. That bubble is lazy. And I don't mean lazy in the way you might be lazy on a Sunday afternoon. I mean lazy in the most fundamental way that nature itself is lazy. And once you understand this laziness, once you truly see what that bubble is doing, you'll never look at the world the same way again. So let me ask you a question that seems simple. Why do bubbles form? No, seriously, why? Because of air pressure, you might say. Wrong. Because soap is slippery? Wrong again. The real answer is far more beautiful, far more strange, and far more fundamental than you've ever imagined. Now, before we talk about bubbles, we need to talk about something more fundamental. We need to talk about the most important idea in all of science. If I had to pass just one sentence to future generations, it would be this. Everything is made of atoms. Little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. You see, in that one sentence, there is an enormous amount of information about bubbles, about water, about everything. Let me show you what I mean. Imagine you're a water molecule. You're sitting there in the middle of a big drop of water, surrounded on all sides by your friends, other water molecules. Now, these molecules aren't just sitting still. Oh, no. They're jiggling, bouncing, moving around like crazy. That's what we call heat. The hotter something is, the more the molecules jiggle. But here's the interesting part. You, as this water molecule in the middle, you're being pulled in all directions equally. Your friend on your left is pulling you left. Your friend on your right is pulling you right. Top, bottom, front, back, you're being pulled equally in all directions. The result? The forces all cancel out. You feel nothing special. You're happy, comfortable, sitting there in the middle of the water. But now imagine you're a water molecule at the surface. Suddenly, everything changes. You still have friends below you pulling you down. You still have friends to your left and right pulling you sideways. But above you? Nothing. Just air molecules, nitrogen, oxygen. And these air molecules barely pull on you at all compared to your water molecule friends. So what happens? You feel an imbalance. You're being pulled down and sideways by your water friends, but there's nothing pulling you up. It's like being in a tug of war where one side has no team. You're pulled inward toward the bulk of the water. Now here's where it gets interesting. Every single molecule at the surface feels this same pull inward. Every single one of them would rather be inside the water than on the surface. And this, my friends, is what we call surface tension. But let me be very clear about something. Surface tension is not a special force. It's not a new kind of physics. It's simply the result of the fundamental attractive forces between molecules being unbalanced at the surface. That's all. But from this simple imbalance, we get the most remarkable consequences. Now, I'm going to tell you something that might sound philosophical, but it's actually the most practical thing in physics. Nature is lazy. What do I mean by this? I mean that every system in nature tries to minimize its energy. It's not that nature wants anything. Nature doesn't care what we think. It's just that systems naturally evolve toward their lowest energy state, like a ball rolling down a hill. And here's the key insight. Molecules at the surface have higher energy than molecules in the bulk. Why? Because they have fewer neighbors to interact with. They're missing those attractive interactions from above. So if you want to minimize the energy of a water system, you need to minimize the number of molecules at the surface. And how do you minimize the number of molecules at the surface? You minimize the surface area. This is profound. The water doesn't know it's supposed to minimize its surface area. It's just that molecules naturally arrange themselves to lower the overall energy. And the mathematical consequence of this is that the surface area becomes as small as possible. Now here's a beautiful mathematical fact. For any given volume, the shape that has the smallest surface area is a sphere, not a cube, not a cylinder, a sphere. So what do we predict? We predict that small drops of water, if they're not being pulled by gravity or sitting on something, should be perfectly spherical. And what do we observe? In zero gravity, water drops are perfect spheres. Even on Earth, tiny droplets of morning dew are nearly spherical. But wait, can we do even better? Can we trap air inside a thin film of water and make a bubble? Now we're getting to something really interesting. Let me try to blow a bubble with pure water. What happens? It doesn't work. The bubble bursts immediately. Why? Here's the problem. Pure water has too much surface tension. The surface tension is so strong that as soon as you try to blow a bubble, the film wants to collapse immediately. It's pulling itself together so strongly that it cannot sustain a thin film. Think about it. A bubble is actually two surfaces, an inner surface and an outer surface. Each surface has surface tension pulling on it. For pure water, this pull is so strong that the film is unstable. Any small disturbance, any tiny imperfection, and bang, the bubble collapses. It's like trying to hold together two rubber bands that are pulling apart with tremendous force. The slightest weakness, and they snap. So now we add soap. And suddenly, miracle, we can blow bubbles. But what is soap doing? This is where most people's logic collapses because the answer is counterintuitive. Soap doesn't make water slippery. Soap doesn't strengthen the water film. In fact, soap does something that sounds completely backwards. Soap reduces the surface tension. Wait, what? Doesn't that make it weaker? Shouldn't that make it even harder to blow bubbles? No. And here's why. Soap molecules are very special molecules. They have two ends, a hydrophilic, water-loving head, and a hydrophobic, water-hating tail. When you add soap to water, these molecules arrange themselves at the surface with their heads in the water and their tails sticking out. Now, when soap reduces the surface tension, it does something crucial. It makes the film more flexible. The film can stretch. It can deform. It can adjust to disturbances without immediately snapping. But there's something even more remarkable. The soap molecules can move. If you stretch one part of the bubble film, soap molecules from other areas rush to that spot, maintaining the surface tension relatively constant across the whole bubble. It's like having a self-healing material. Now let's talk about pressure, because this is where things get really interesting. Inside the bubble, we have air pressure pushing outward. This makes sense. The air wants to expand. But we also have surface tension pulling inward, trying to minimize the surface area. For the bubble to exist, these forces must balance. But here's something subtle. A bubble actually has higher pressure inside than outside. Why? Because of the surface tension. The surface tension creates an additional inward pressure. The mathematical relationship is beautiful. The pressure difference between inside and outside is given by delta P equals 4 gamma over R, where gamma is the surface tension and R is the radius of the bubble. Notice the factor of 4? That's because a bubble has two surfaces, inner and outer, and each contributes 2 gamma over R. This formula tells us something remarkable. Smaller bubbles have higher pressure inside. If you blow two bubbles of different sizes and connect them, the smaller bubble will blow up the larger one. It sounds backwards, but it's true. The smaller bubble has higher internal pressure. So now we can answer the question completely. Why are bubbles spherical? A bubble is trying to minimize its surface area for a given volume of air. This is because minimizing surface area minimizes the energy associated with surface tension. The shape that minimizes surface area for a given volume is a sphere. Therefore, bubbles are spherical. But notice what's happening here. The bubble isn't trying to be spherical. The bubble doesn't know about geometry or calculus. The bubble is simply the result of millions of molecules, each one being pulled by its neighbors, each one jiggling around, and collectively, through the fundamental laws of physics, they arrange themselves into the shape that we mathematically predict. This is the beauty of physics. From simple rules, molecules attract when apart, repel when too close, we can predict complex behavior. We can understand why bubbles are round, why they have colors, why they pop. And speaking of colors, have you ever wondered why bubbles show those beautiful swirling colors? This is yet another profound piece of physics: interference. The bubble film is very thin, comparable to the wavelength of light. When light hits the bubble, some reflects from the outer surface and some from the inner surface. These two reflected waves interfere with each other. Depending on the thickness of the film at any point, different colors interfere constructively or destructively. As the bubble drains and the film thickness changes, the colors swirl and change. When the bubble is about to pop, you see black patches. These are regions where the film is so thin, less than the wavelength of light, that destructive interference occurs for all visible wavelengths. So every bubble is not just a physics demonstration of surface tension. It's also a demonstration of wave interference, of the wave nature of light. But here's what I really want you to take away from this. The bubble doesn't know physics. The bubble is just atoms obeying the fundamental rules. And yet from these simple rules, we get this complex, beautiful behavior. This is what I love about physics. We don't just describe what we see, we explain why it must be that way. We show that the sphere isn't arbitrary, it's necessary. Given the rules about atomic forces and energy minimization, bubbles must be spherical. There's no other option. And this way of thinking, this way of going from fundamental principles to observed phenomena, this is the essence of physics. You start with the simplest ideas. Atoms attract and repel. From this, you derive surface tension. From surface tension, you predict spherical bubbles. From spherical bubbles, you understand pressure differences. Every step follows logically from the one before. So the next time you see a child blowing bubbles in the park, I want you to see it differently. You're not just watching bubbles, you're watching a demonstration of molecular forces, of energy minimization, of mathematical optimization, of wave interference. That bubble is solving problems that would take supercomputers to calculate explicitly. It's finding the minimal surface for a given volume. It's balancing surface tension against pressure. It's demonstrating the laziness of nature, the tendency of systems to minimize energy. And it's doing all of this effortlessly, beautifully, in real time. This is why I love physics. Because once you understand the fundamental rules, once you really see how atoms work, you realize that the entire world is full of miracles. Not supernatural miracles, but the miracle of complexity emerging from simplicity. The miracle of mathematical beauty underlying physical reality. The bubble isn't just round because that's how bubbles are. The bubble is round because of the quantum mechanical forces between molecules, because of the statistical mechanics of molecular motion, because of the mathematical fact that spheres minimize surface area. And if we can understand something as simple as a bubble at this deep level, imagine what else we can understand. Imagine what other phenomena which seem mysterious and complex are actually just the logical consequence of simple, fundamental rules. So, why do bubbles form? They form because soap reduces surface tension enough to allow thin films to exist. Why are they round? Because spheres minimize surface area, which minimizes energy. Why do they pop? Because the film drains, becomes too thin, and can no longer sustain the pressure difference. But more importantly, how do we know all this? Because we started with atoms. We understood the forces between them. We worked out the consequences step by step. We made predictions, and nature confirmed them. This is the power of physics. This is the beauty of understanding nature from first principles. And all of this profound physics is right there in a simple soap bubble floating in the afternoon sun, waiting for anyone with curiosity to see it. That's what I uncovered. Not that bubbles are round, everyone knew that. But why they must be round, why they form, why soap is necessary. I uncovered the chain of logic from atomic forces to the perfect sphere floating before your eyes. And once you see it, once you really understand it, your logic doesn't collapse. It expands. It grows to encompass a more beautiful, more connected, more profoundly simple view of the universe. That's the real miracle.